Hello, my name is Yusopar from Segang University. I will present our paper, Gradient Knows Best, Mixed Precision Quantization via Gradient Guided Bit Allocation for Super Resolution. This work focuses on post-training mixed precision quantization for image super resolution models. The key idea is to allocate layer-wise bit widths based on gradient-based sensitivity. Low bit quantization is essential for efficient SR, but uniform bit allocation ignores layer-wise sensitivity differences. To solve this, MPQ assigns different bit widths to different layers. Existing PTQ-based MPQ method estimate layer sensitivity using static activation statistics. However, these statistics does not always reflect the actual quantization error. The example on the bottom left showed that STD and SQNR are not consistently correlated. Another problem is the batch normalization-free structure of SR models, which is often used to preserve high-frequency details. Without BN, sample and channel-wise activation range vary, leading to clipping or wasted dynamic range. The example on the bottom right illustrates this variance imbalance caused by BN removal. To address these two problems, the paper proposed three main components: gradient-guided bit allocation, dynamic activation range normalization, and bit-aware fine-tuning. Overall, the framework follows three stages. First, the quantization bounds are initialized using a small calibration dataset. Then, GBA estimates layer-wise sensitivity and assigns appropriate bit width. Finally, with the assigned bit width fixed, bit-aware fine-tuning optimizes the quantization range for weight and activation. Now I will explain GBA in more detail. The goal of GBA is to allocate layer-wise bit width based on the actual reconstruction loss sensitivity. Instead of using static statistics, GBA introduced a learnable continuous bit offset for each layer. The bottom illustration shows the intuition of GBA. A smaller gradient means that increasing the bit width can reduce the loss more effectively. Therefore, GBA assigns higher bit width to layer with smaller bit offset gradient. The GBA process has four main steps. First, the method introduces a continuous bit offset parameter for each layer. This offset is added to the base bit width to determine the final bit width. Second, the method computes gradient of the reconstruction and feature loss with respect to the bit offset. Third, layers are ranked according to the gradient-based sensitivity. Finally, the continuous bit offset are converted into discrete bit offset. Dynamic activation range normalization targets BM-free SR models where activation range vary across samples and channels. DEN normalizes each activation channel to the range from -1 to 1 before quantization. After quantization, it restores the original scale through denormalization. This process preserves the original activation scale while making the quantization range more stable. In bit-aware fine-tuning, the bit widths are fixed and only the quantization range for weights and activation are optimized. This makes the optimization efficient, and fine-tuning is performed for only two epochs using the reconstruction loss and feature loss shown below. This slide shows quantitative results on CNN-based SR models, including EDSR and RDN. The experiments are conducted under 3-bit and 4-bit quantization. Compared with previous PTQ method, the proposed method consistently achieves higher PSNR and SSIM. This slide shows results on the transformer-based SR model SwinIR. The proposed method also improved PSNR and SSIM on SwinIR compared with previous PTQ methods. This shows that our methods are not limited to the CNN-based SR models, but can also be applied to the transformer-based SR architectures. This slide shows qualitative comparison on the Urban 100 dataset. Compared with previous quantization methods, the reconstructed image from our method preserve sharper structure and clear textures. Finally, this slide shows the ablation study. The paper analyzed the effects of weight GPA, activation GPA, and DAN. The results show that activation GPA and DAN provide large performance gains, and adding weight GPA further improves the final performance. Overall, the ablation study confirmed that each component contributed to the final performance improvement. Thank you for listening. If you have any questions, please contact us.